Hello, my name is Dr. Abrahamian, and this is part 2 of my video series on single variable calculus 2 that I teach at University of Maryland. In this video, we're going to talk about volumes using the cylindrical shell method, and these are all applications of integral. So here's an example. Find the volume of the solid obtained by rotating the region underneath the curve y equals x squared minus x cubed from x equals 0 to x equals 1 about the y-axis. So first thing we're going to do is we're going to attempt to solve this problem using the methods that we have learned before, using the cross-section method. So first we have to graph this. So this is y equals x squared minus x cubed. I can factor x squared, and that gives you 1 minus x. So in this interval, when x is between 0 and 1, this entire thing is always greater than or equal to 0. We do have two intercepts. The intercepts are x equals 0 and x equals 1. So the graph would roughly look like this. Now notice that at 0, it is tangent. The graph is tangent because we have x squared. So they're talking about this region. So we can rotate this about the x-axis. So we have to reflect this to the other side, and we get a shape like this. Now, if we were to use the cross-section method, we'll have to find this top of the curve and look at the cross sections that are horizontal cross sections, because the rotation is done about the y-axis. These are the cross sections. So cross sections are washers, and in order to find the area of a washer, we need to find the inner radius and the outer radius. So volume in this case is going to be integral from 0 to whatever this top is. I'm going to call that A, and we can find that that's just the critical point of the curve. A of y dy. A of y is the area of the washer at y. Now, if you look at the curve, I'm going to draw that again. How do we find the area of the washer? We need to look at the curve, and we need to find the inner radius and the outer radius. So these are the inner and outer radius. The red one is the inner radius, and the green one is the outer radius. So this is the outer radius. And we need to find these two in terms of y, and y is right here. So what are these values? So we need to find the inner and outer radii in terms of y. But what are these? Well, those are the x coordinates. So these are x coordinates of points on y equals x squared minus x cubed. So what does that mean? In other words, we need to solve that equation. So in other words, we need to solve y equals x squared minus x cubed for x. But this is cubic, and we can't really solve cubics. The process of solving cubics is too complicated. So solving cubics is not easy. So we have an easy formula for quadratics, but there is no easy formula for cubics, which means we need a different method in finding the volume of the solid that we were discussing. So how do we deal with that? So the idea is, instead of looking at the cross sections and instead of looking at these cylinders, so we looked at cylinders with a small thickness here and integrate with respect to x, we will look at something else called a cylindrical shell. So the idea is to cover the solid by cylindrical shells. Now, what are cylindrical shells. Cylindrical shells are solids between two cylinders. So what is a cylindrical shell first? So a cylindrical shell is a solid between two cylinders that have a common axis. So we cover our solid with these cylindrical shells, and then we add up the area, the volumes of these cylindrical shells. So the first step would be to figure out what's the volume of a cylindrical shell. So let's draw a cylindrical shell. So we have an inner cylinder here, and then we have an outer cylinder here. And the cylindrical shell is whatever is in between these two. So I'm going to mark the region that we call a cylindrical shell. This in between these two is what we call a cylindrical shell. So it's everything between these two cylinders. Okay, let's figure out what's the volume of this. Well, we know the volume of a cylinder. So we take the volume of these two cylinders and then we subtract them. Let's say this radius is R1, the inner radius, and let's say the outer radius is R2. So the volume of the cylindrical shell is going to be volume of the larger cylinder, which is pi R2 squared. So that's the area of the base times the height. Now let's say the height is h minus pi r1 squared times h. Let's do a little bit of simplification here. So we're going to factor a pi. We get r1 squared, r2 squared minus r1 squared, and then we also have h. We are going to use difference of squares. So pi r2 minus r1, r2 plus r1, and then times h. Now this is basically delta r. So I'll put that at the end, r2 minus r1. And I'm going to write this down as pi r2 plus pi r1 and then h. Now notice that this guy is basically the circumference. So we can write this down as 2 pi r2 plus 2 pi r1 over 2. So what is this? This is average circumference. So it's average circumference of the outer circle and the inner circle. And then multiplied by h. H is the height. And then multiplied by R2 minus R1. If you look at the cylindrical shell, R2 minus R1 is basically the thickness. It's this piece right here. So this is delta R, or R2 minus R1. So that's the thickness. So in other words, the volume of a cylindrical shell is circumference, height, and thickness. So in order to solve the problem, we will have to take our solid, cover it with a bunch of cylindrical shells, and add up those. Let the number of cylindrical shells to go to infinity, and that would give us an integral, a definite integral. So we have something like this. Let me draw the solid. So we're going to cover this one with these cylindrical shells. So this is one cylindrical shell. It's the region between two cylinders. This is very, very thin, a thin cylindrical shell. Then we'll do another one next to it, then we'll do another one. So I'll just show you a couple more of these. And then maybe another one I'll draw right here. So as you put together all of these cylindrical shells, at the end it would be basically infinitely many of these, you get the volume. So the formula for the volume then becomes circumference, height, thickness. This is the formula for the volume using the cylindrical shell method. So now let's solve the problem that we started at the beginning. So solution to example 2.1 up there. Okay, so the volume is going to be the integral. First thing is circumference. So what is the circumference? Let's look at this. Let's look at the cylindrical shell. Well, the cylindrical shell that we have, the radius is exactly x. This radius is the x value. So x is the radius. Therefore, circumference is 2 pi x. So this is circumference multiplied by the height. The height here is the y coordinate. And what is the y coordinate? Y coordinate is given by x squared minus x cubed. So this is the height. And then we have thickness. So what is the thickness here? The thickness is delta x. So it would be dx. And then the range for x, which we know it goes from 0 to 1 because we are rotating the portion between x equals 0 and x equals 1. And this is an easy integration. So we're going to factor 2 pi. It is a constant. We get integral from 0 to 1. We are going to distribute x. We get x cubed minus x to the fourth dx. Next, we're going to integrate. So we get 2 pi x to the fourth over 4 minus x to the fifth over 5 from 0 to 1. And that gives us 2 pi times 1/4 minus 1/5. And we can simplify this to get pi over 10, I believe. Because this one becomes 1 over 20 multiplied by 2, you get 1 over 10. So we get pi over 10 as the volume of the solid that they gave us. Now, in general, if you have a region that lies between two curves, so let me draw a diagram for this. So let's say I have this curve y equals f of x, and I have another curve down here y equals g of x, and I rotate this about the y-axis. I can evaluate the volume using circumference, height, thickness. So let's kind of see where the circumference, height, thickness is. I'm going to look at a sample cylindrical shell. So one of these shells looks like this. So we have to look at the circumference, thickness, and height. What is the circumference? Well, the circumference, the radius is x, therefore the circumference is 2 pi x. What is the height? The height is the difference between f of x and g of x, so it's f of x minus g of x. And thickness is dx, and the limits of x are from a to b. So to summarize, cylindrical shell method tells us that the volume is integral of circumference, height, and thickness. And that brings me to the end of this video. So I will see you in the next video.